Nothing. Don't worry about it. What law of physics is conservation of momentum the same as? Well, for momentum, we're just going to say it's the same thing as Newton's third law. We all remember Newton's third law because it is useful to us in our problem solving. What do you mean you don't remember Newton's third law? We talked about it for several weeks. Remember, if A pushes B, then B pushes A, in equal and opposite, equal magnitude and opposite direction. You have to have two objects for Newton's third law to exist. You can't just have an individual object. Same thing for conservation of momentum. You have to have two objects doing something. Continuing on, we are going to do another derivation. This time for the derivation of conservation of momentum. For each line in the derivation, explain what mathematically was done. Remember what a derivation is. Deriving an equation just means showing the steps on how you got to them. For this one, we're showing the steps starting with an equation that we already know, which is what we do when we derive. We look at our equation sheet and we say, okay, what equation do we know? We know if B exerts a force on object A, then A exerts a force on object B in an equal magnitude and opposite direction. So negative F1 on 2 equals F2 on 1. That's the same thing as Newton's third law. Just what we have right there. So we start with Newton's third law, which states that force 1 on 2 is equal and opposite to that of 2 on 1. How am I going to move this thing? There we go. Next up, we plugged in Newton's second law. F equals ma, right? So we can just substitute m and a, keeping our subscripts, making sure everything is still making sense. Next up, we get this fraction here. Where the heck did that come from? We plugged in a equals delta v over delta t. And delta means final minus initial. So just using our standard equation that's in our head, not even on our equation sheet, we were able to do that. Next up, we would multiply each side by t. What that does for us is it cancels out the t. Now time is no longer required. If we kept t involved, then we'd be talking probably about impulse, right? But not this time. Next, we're going to distribute the m's. So m2 is going to be multiplied by v2f and v2i, and then m1 is v1f and v1i. Then finally, we added the negative terms to the opposite side to make them positive. There you go. What two equations express conservation of momentum in two dimensions? Well, remember, when we're dealing with any vector in two dimensions, we have to separate those two dimensions. So we will have x equation and we will have y equation. We do the same thing as we did with projectile motion. Keep the x separate from y. So for the x equation, remember how many subscripts were in the previous videos? Hold on to your boots. m1 v1 not in the x direction plus m2 v2 not in the x direction equals m1 v1f in the x direction plus m2 v2f in the x direction. You will never believe what the y equation is going to look like. It's going to be m1 v1 not y. Are you still watching this? m2 v2 not y equals m1 v1f y plus m2 v2f y. Woo!